Okay, so as front-end developers, we often bask ourselves in the technology of today and tomorrow. We live in exciting times where we need to new technological advancements come up every day. But today, I want to take you back in time, back before we were counting gigabytes, or even the existence of JavaScript. Back to 1989, where some of us are not even born and appreciate the technologies of the past. So today we are talking about the Game Boy. We're not talking about the Switch, not the Nintendo DS, not the Game Boy Advance, not the Game Boy Color, but this. The original Nintendo Game Boy, first released in Japan on April 21st, 1989. So this device has 160 by 144 pixels. It is just 4 colors. There is no backlighting, so they sold lighting peripherals, and more peripherals such as stereo sound. The Game Boy itself has only one speaker, but it actually outputs stereo sound through the headphone jack. So in order to hear like stereo, you need to put some extra stuff. So there were only the A and B buttons on it, unlike its successors, which introduced the additional X and Y buttons. It is also powered by 4 AA batteries. So on the chip, we have one general processor, one pixel processor, 2 RAM components, one for the CPU and another for the video data. For the ROM components, there's 256 bytes of bootstrapping code. The rest of it, known as the game data, is actually on the cartridge, if you didn't know. So a short refresher on your computer architecture. In a typical computer systems, there should be a CPU, a memory, and input and output. So the information is strictly passing through the different buses. So a closer look at the CPU. It is made by Sharp, same manufacturer of the manufacturer of TVs. I didn't know that they have a history with Nintendo. The processor architecture is similar to Z80, what the Pac-Man arcade cabinet ran on. It is also similar to the Intel 8080, which was a popular home PC. So the functions of a CPU, it is supposed to read information, decode information, execute, and perform all of these instructions really fast. So it runs at an amazing speed of 4.19 megahertz. So 30 years ago, it was pretty quick. The 8 bits on the CPU is the bus size. The instruction size will be a word, 8 bits. In other words, roughly 256 instructions available. So this also means that the CPU can only receive or transfer 8 bits worth of data every cycle. So in the CPU, there are 8 registers to store information. Each can store up to 1 word or 8 bits. So the general registers in the CPU are 1 word each. Most of the instructions will work with 1 register. However, sometimes we feel that counting from 0 to 255 is not enough. So luckily, there are some instructions that work with 2 registers. So the processor allows us to pair up some of the registers. With that, we can operate with 2 words and 16-bit. That means that we can now count up to 56,000 instead of just 250. So the bootloader is exactly 256 bytes. It is also the first piece of code ran when you first boot up the system. It is also responsible for setting everything up that is required. Something like the setting initial state of the machine. Now a quick review of what are the things the bootloader does. So the piece of code in yellow, it sets up the program stack. It's used for tracking and managing function calls. It initializes the VRAM to be all 0. It sets up the audio settings with their default flags, and finally the graphic color palette. So the next part loads the Nintendo logo, but it loads from the cartridge. So something to think about here. What happens if you don't put in the cartridge?
Let's play, right?
Correct. So the Nintendo logo doesn't appear. It's just 2 black bars, and you can also notice a small patch on the right side. So it is actually the all-right reserve symbol. But why did they not include the Nintendo logo on the bootloader? It's weird, right? I mean, for something that is always shown to the user, why waste space on the cartridge itself? So it turns out that we can answer this question later. So with all the necessary data loaded into the video RAM, the next chunk of code is all about this. Okay, drawing and scrolling the logo down, and then playing the iconic ping sound. Okay, those good memories. So the white section of the code is the data for the Nintendo logo. Okay, remember a few slides ago that we discovered that we have loaded the logo data from the cartridge. And know why is this identical data right there in the bootloader itself? Memory is a huge problem. What other possible reasons can there be? So it turns out that Nintendo has filed a logo as a trademark. So what does this mean? It is illegal to possess or distribute a trademark, meaning that if you're not licensed by Nintendo, you cannot have this logo on your cartridge. So it's simple, right? You don't include the cartridge, the logo in the cartridge, right? Problem solved. Okay, it turns out no. So this green section of the code, it does a comparison of its own logo against the cartridge logo. So if any bytes doesn't match up, it locks up. And then you only see this. And it stops there forever. So meaning that you cannot play a game no matter how hard you blow onto your cartridge. Back to our registers. The stack pointer is where we store our local variable data whenever we call a function. Because there's only a limited number of registers available in the CPU, we need to save them somewhere before we call another function. So when you're not writing in assembly, you can simply declare your local variables and call the functions. But when you're writing in assembly, you need to be aware of how many local variables you have created and store them back in the stack before you call a different function. So remember, you have to restore back when you return from the function. The other special registers is called the program counter. It keeps track of where in the memory should the CPU read the next instruction from. If the instruction is one word, it reads another byte as data input. Then you advance the current PC by 2. Because you read one as your instruction, the next one is your data, so it's supposed to move by 2. So this brings us to the next problem. What is our addressable memory size? So with the program counter being 16 bits, the CPU can only access the memory address at 000 to 4Fs, which is 16 bits. But what if we need to if we can only reference up to 4Fs, which is 16 bits, does it mean that the game sizes cannot be more than 64 kilobytes? Because that's what 16 bits can represent. So let's take a look at some of the more popular games on Game Boy. The Pokemon Blue is 1 megabyte, so it doesn't fit. The Tetris is 32 kilobytes, so it definitely fits. And the Super Mario is 64 kilobytes, so it kind of fits. So if we take Super Mario as our ROM, and then put it into our addressable space, okay, it fits exactly nice, right? But what about the RAM and the VRAM, all of which has to be represented within the same data? So the answer is paging. For those who do not remember, it is a strategy where you can retrieve the data from the larger secondary storage. So this works roughly the same way, but it's called banks in the Game Boy. So ROMs are split into numbered banks of 16 kilobytes. So how do you select them? By writing onto the ROM. Okay, you heard me right? By writing onto the read-only memory. So because those data cannot be changed, when you want to write to a ROM, it simply means that you want to do something different, right? So for this case, it means that you want to read a different ROM. It is designed for you to write 7 different bits onto different part of the ROM to signify what ROM you want to read. So this means that we have a theoretical maximum number of banks possible at 180 banks, which is roughly 2 megabytes. So the largest possible games is actually 2 megabytes. So this is also why you see Tetris, Pokemon, and Super Mario in a power of 2, because you can only represent them in bits, which is multiples of 2. So we have seen Game Boys handle larger game sizes. So what about saving and loading game data? So we can swap our cartridge to another Game Boy machine, and our save data will be found on the new Game Boy machine, correct? So this means that the game save data is actually on the cartridge itself. Solid state drive is extremely expensive during that time. So what other solutions could they have made to store the data? So anyone here has their games being unable to save their data after a few years? Yeah, even if you blow into the cartridge? Okay, that's because the battery ran out of juice. Okay, so there's a battery on the cartridge itself, and it acts as a power supply to keep the RAM alive. So you can see the battery here, and there. But not all cartridges needed to retain the data on the board. So for this case, the Bomberman and Tetris, they don't have a battery, and they have much lesser components. So what are the other components on it, aside from the battery? The memory bank controller, which does the dynamic mapping of the ROMs. Yeah. So for information, there is even a guide on iFixit to replace the battery. So there is the RAM, where you keep your saved data, and it also acts as the external RAM for the CPU to use. So let's go back to the memory chart. So over here, we have our internal RAM within the space. So each of them is up to 8 kilobytes. So this is where the internal RAM goes and the VRAM goes. And for an external RAM, it sits there. So now the chip that is responsible for translating data is performed by this thing called the pixel processing unit, whatever that you see being rendered on the screen. So if we go back and take a look at the specs, the LCD display is 160 pixel wide, 144 pixels tall. So there are 4 different colors available. It is just 4 different terrible shades of green. So it has its own memory of 8 kilobytes. The way images are represented is by their bits. So for instance, 1 byte of hex in 62, it will become this. If you read the individual bytes from left to right, where if it is a 0, it is a white, and if it's a 1, it will be a black, you get this. 1 pixel of white, followed by 2 pixels of black, 3 pixels of white, 1 pixel of black, and 1 pixel of white. But the LCD has 4 different colors. So they added another byte for it. So now we have 2 bytes to represent 4 different colors. And if you plot them as 8 by 8 pixels and add a few more rows of byte, you'll get a Goomba. So it is exactly 8 by 8 pixels and conventionally called a tile. So the LCD consists of 160 by 144 pixels. Again, it means 20 by 18 tiles arranged. So let's take a look at this. So we can somehow identify the tiles, right? And with some help, you can still clearly see that everything in this screen is constructed from tiles. So how about this screen? Again, with the overlay, you can see that it's constructed through tiles. So another interesting thing that the screen has is that it can be shifted around. So seemingly giving the illusion of scrolling, something that is used a lot in side-scrolling games, like Metroid and Super Mario. So in both games, you see that the screen is scrolling towards the left. Something to note, the data off screen is actually still there, just that it is not rendered. The other way of drawing on the screen is a fixed window. This window allows you to draw over the screen. So think of it as a div with the Z index set to 10. The position absolute, and it doesn't move the screen. So it has its own independent position. So the other feature of this window is that you can also move it around. So for instance, moving around to the top and moving to the right. So some of you have already realized how this can be used. Right? So in games that have a moving background, you want a certain part of the screen to display static, for instance, to show points. You can utilize the fixed window. So DuckTales, the games on your left, it has a score and statistic rendered as a fixed window. The main background is then rendered with the screen. So now we have the background and a fixed window. So what about the duck and the Italian farmer, who is not moving along with either of the fixed window or background. So this means that there should be a third way of drawing onto the screen, right? So this third way is actually called the Sprites attribute table, weird name. Similarly, it can be used as a tile system like before, but with additional fields, such as location. So there are 40 slots available in the table. You can have up to 40 different independent sprites on the screen. However, due to hardware limitations, you can only have up to 10 tiles on every line. So this is what that will actually be drawn. The other 5 Pokemon's trainer will not be drawn because a sprite is still a tile. So for this case, the Pokemon render actually takes up 2 tiles per line. And to render 5 trainers on the same line, we'll need 10 in total. So we cannot exceed more than 10. So meaning that if you have one Goomba dropping down, the Goomba will be rendered like this. It will ignore the rightmost sprites. So, but with this limitation, game developers have came out with a novel way to draw more than 10 lines per sprite. So this game is Contra Operation C for the Nintendo Game Boy. So as you can see, the flashing sprites is not a bug, but a feature. So what the developer did was to selectively omit tiles and alternate the rendered tiles in the next frame. So in other words, the screen is not rendered all the tiles at the same time, and it's not breaking the rule of 10 tiles per line. So isn't this amazing? Okay, so and with this, I hope they gain some insight onto the beautiful things of Nintendo Game Boy. Thank you.